deals with varieties of matter and change of one kind of matter into the other. Transformation of matter from one kind into another occurs through the various types of reactions. One important category of such reactions is redox reactions. A number of phenomena, both physical as well as biological, are concerned with redox reactions. These reactions find extensive use in pharmaceutical, biological, industrial, metallurgical and agricultural areas. The importance of these reactions is apparent from the fact that burning of different types of fuels for obtaining energy for domestic, transport and other commercial purposes, electrochemical processes for extraction of highly reactive metals and non-metals, manufacturing of chemical compounds like caustic soda, operation of dry and wet batteries and corrosion of metals fall within the purview of redox processes. Of late, environmental issues like hydrogen economy, use of liquid hydrogen as fuel, and development of ozone hole have started figuring under redox phenomenon. 8.1 Classical idea of redox reactions. Oxidation and reduction reactions. Originally, the term oxidation was used to describe the addition of oxygen to an element or a compound. Because of the presence of dioxygen in the atmosphere, 20%, many elements combine with it, and this is the principal reason why they commonly occur on the Earth in the form of their oxides. The following reactions represent oxidation processes according to the limited definition of oxidation: 2 Mg S plus O2 G 2 MgO S 8.1 S S plus O2 G SO2 G 8.2. After studying this unit, you will be able to identify redox reactions as a class of reactions in which oxidation and reduction reactions occur simultaneously. Define the terms oxidation, reduction, oxidant, oxidizing agent, and reductant, reducing agent. Explain mechanism of redox reactions by electron transfer process. Use the concept of oxidation number to identify oxidant and reductant in a reaction. Classify redox reaction into combination, synthesis, decomposition, displacement and disproportionation reactions. Suggest a comparative order among various reductants and oxidants. Balance chemical equations using I. Oxidation number 2. Half reaction method. Learn the concept of redox reactions in terms of electrode processes. Unit 8 Redox reactions. Where there is oxidation, there is always reduction. Chemistry is essentially a study of redox systems. 2019-20. (264) Chemistry in reactions. 8.1 and 8.2. The elements magnesium and sulfur are oxidized on account of addition of oxygen to them. Similarly, methane is oxidized owing to the addition of oxygen to it. CH4, G, plus 2O2, G, CO2, G, plus 2H2O, L. 8.3. A careful examination of reaction. 8.3. In which hydrogen has been replaced by oxygen prompted chemists to reinterpret oxidation in terms of removal of hydrogen from it, and therefore, the scope of term oxidation was broadened to include the removal of hydrogen from a substance. The following illustration is another reaction where removal of hydrogen can also be cited as an oxidation reaction. 2H2S, G, plus O2, G, 2S, S, plus 2H2O, L. 8.4 As knowledge of chemists grew, it was natural to extend the term oxidation for reactions similar to 8.1 to 8.4, which do not involve oxygen but other electronegative elements. The oxidation of magnesium with fluorine, chlorine and sulfur etc. occurs according to the following reactions: Mg, S, plus F2, G, MgF2, S, 8.5, Mg, S, plus Cl2, G, MgCl2, S, 8.6, Mg, S, plus S, S, MgS, S, 8.7, incorporating the reactions, 8.5 to 8.7, within the fold of oxidation reactions encouraged chemists to consider not only the removal of hydrogen as oxidation, but also the removal of electropositive elements as oxidation. Thus the reaction 2K4 Fe Cn 6 Ac plus H2O2 Ag 2K3 Fe Cn 6 Ac plus 2KOH Ac is interpreted as oxidation due to the removal of electropositive element potassium from potassium ferrocyanide before it changes to potassium ferricyanide. To summarize, the term oxidation is defined as the addition of oxygen electronegative element to a substance or removal of hydrogen electropositive element from a substance. In the beginning, reduction was considered as removal of oxygen from a compound. However, the term reduction has been broadened these days to include removal of oxygen electronegative element from a substance or addition of hydrogen electropositive element to a substance. According to the definition given above, the following are the examples of reduction processes: 2HgO, S, 2Hg, L, plus O2, G. 8.8 Removal of oxygen from mercuric oxide, 2FeCl3, Ac, plus H2, G. 2FeCl2, Ac, plus 2HCl, Ac. 8.9 Removal of electronegative element, chlorine from ferric chloride, CH2 is equal to CH2, G, plus H2, G, H3CCH3, G. 8.10 Addition of hydrogen, 2HgCl2, Ac, plus SnCl2, Ac, Hg2Cl2, S, plus SnCl4, Ac. 8.11 Addition of mercury to mercuric chloride, in reaction, 8.11 Simultaneous oxidation of stannous chloride to stannic chloride is also occurring because of the addition of electronegative element chlorine to it. It was soon realized that oxidation and reduction always occur simultaneously, as will be apparent by re-examining all the equations given above. Hence, the word redox was coined for this class of chemical reactions. Problem 8.1 In the reactions given below, identify the species undergoing oxidation and reduction: I, H2S, G, plus Cl2, G, 2HCl, G, plus S, S, 2, 3Fe3O4, S, plus 8L, S, 9Fe, S, plus 4L2O3, S, 3, 2Na, S, plus H2, G, 2Na, S. Solution: I, H2S is oxidized because a more electronegative element, chlorine, is added to hydrogen, or a more electropositive element, hydrogen, has been removed from S. Chlorine is reduced due to addition of hydrogen to it. 2. Aluminium is oxidized because oxygen is added to it. Ferrous ferric oxide 2019-20. 265 Redox reactions, Fe3O4, is reduced because oxygen has been removed from it. 3. With the careful application of the concept of electronegativity only we may infer that sodium is oxidized and hydrogen is reduced. Reaction 3, chosen here prompts us to think in terms of another way to define redox reactions. 8.2 Redox reactions. In terms of electron transfer reactions, we have already learned that the reactions 2 Na S plus Cl2 G 2 Na Cl S 8.12 4 Na S plus O2 G 2 Na 2O S 8.13 2 Na S plus S S Na 2 S S 8.14 are redox reactions because in each of these reactions sodium is oxidized due to the addition of either oxygen or more electronegative element to sodium. Simultaneously, chlorine, oxygen and sulfur are reduced because to each of these, the electropositive element sodium has been added. From our knowledge of chemical bonding we also know that sodium chloride, sodium oxide and sodium sulfide are ionic compounds and perhaps better written as Na plus Cl, S, Na plus 2O2, S, and Na plus 2S2, S. Development of charges on the species produced suggests us to rewrite the reactions 8.12 to 8.14 in the following manner. For convenience, each of the above processes can be considered as two separate steps, one involving the loss of electrons and the other the gain of electrons. As an illustration, we may further elaborate one of these, say, the formation of sodium chloride. 2 Na S 2 Na plus G plus 2ECl2 G plus 2E2Cl G. Each of the above steps is called a half reaction, which explicitly shows involvement of electrons. Sum of the half reactions gives the overall reaction 2 Na S plus Cl2 G 2 Na plus Cl S or 2 Na Cl S. Reactions 8.12 to 8.14 suggest that half reactions that involve loss of electrons are called oxidation reactions. Similarly, the half reactions that involve gain of electrons are called reduction reactions. It may not be out of context to mention here that the new way of defining oxidation and reduction has been achieved only by establishing a correlation between the behavior of species as per the classical idea and their interplay in electron transfer change. In reactions 8.12 to 8.14, sodium, which is oxidized, acts as a reducing agent because it donates electron to each of the elements interacting with it and thus helps in reducing them. Chlorine, oxygen and sulfur are reduced and act as oxidizing agents because these accept electrons from sodium. To summarize, we may mention that oxidation, loss of electron, S, by any species. Reduction, gain of electron, S, by any species. Oxidizing agent, acceptor of electron, S. Reducing agent, donor of electron, S. Problem 8.2 justify that the reaction 2 Na S plus H2 G 2 Na S is a redox change. Solution. Since in the above reaction the compound formed is an ionic compound, which may also be represented as Na plus H, S, this suggests that one half reaction in this process is 2 Na S 2 Na plus G plus 2E 2019 to 20. (266) Chemistry, and the other half reaction is H2 G plus 2E2H G. This splitting of the reaction under examination into two half reactions automatically reveals that here sodium is oxidized and hydrogen is reduced. Therefore, the complete reaction is a redox change. 8 February 2001 Competitive electron transfer reactions place a strip of metallic zinc in an aqueous solution of copper nitrate as shown in Fig. 8.1, for about 1 hour. You may notice that the strip becomes coated with reddish metallic copper and the blue color of the solution disappears. Formation of Zn2+ ions among the products can easily be judged when the blue color of the solution due to Co2+ has disappeared. If hydrogen sulfide gas is passed through the colorless solution containing Zn2+ ions, appearance of white zinc sulfide, ZnS can be seen on making the solution alkaline with ammonia. The reaction between metallic zinc and the aqueous solution of copper nitrate is ZnS plus Co2+ Ac Zn2+ Ac plus Co S 8.15. In reaction 8.15, zinc has lost electrons to form Zn2+ and, therefore, zinc is oxidized. Evidently, now if zinc is oxidized, releasing electrons, something must be reduced, accepting the electrons lost by zinc. Copper ion is reduced by gaining electrons from the zinc. Reaction 8.15 may be rewritten as, at this stage we may investigate the state of equilibrium for the reaction represented by equation 8.15. For this purpose, let us place a strip of metallic copper in a zinc sulfate solution. No visible reaction is noticed and attempt to detect the presence of Co2+ ions by passing H2S gas through the solution to produce the black color of cupric sulfide, CuS, does not succeed. Cupric sulfide has such a low solubility that this is an extremely sensitive test, yet the amount of Co2+ formed cannot be detected. We thus conclude that the state of equilibrium for the reaction 8.15 greatly favors the products over the reactants. Let us extend electron transfer reaction now to copper metal and silver nitrate solution in water and arrange a setup as shown in Fig. 8.2. The solution develops blue color due to the formation of Co2+ ions on account of the reaction. Fig. 8.1. Redox reaction between zinc and aqueous solution of copper nitrate occurring in a beaker. 8.16. Here, CuS is oxidized to Co2+, Ac, and Ag+, Ac, is reduced to Ag,S. Equilibrium greatly favors the products Co2+, Ac, and Ag,S. By way of contrast, let us also compare the reaction of metallic cobalt placed in nickel sulfate solution. The reaction that occurs here is 8.17, 2019-20. 267 Redox reactions. Fig. 8.2 Redox reaction between copper and aqueous solution of silver nitrate occurring in a beaker. At equilibrium, chemical tests revealed that both Ne2+, Ac, and Co2+, Ac, are present at moderate concentrations. In this case, neither the reactants, CoS, and Ne2+, Ac, nor the products, Co2+, Ac, and Ne,S, are greatly favored. This competition for release of electrons incidentally reminds us of the competition for release of protons among acids. The similarity suggests that we might develop a table in which metals and their ions are listed on the basis of their tendency to release electrons, just as we do in the case of acids to indicate the strength of the acids. As a matter of fact, we have already made certain comparisons. By comparison, we have come to know that zinc releases electrons to copper and copper releases electrons to silver, and therefore, the electron releasing tendency of the metals is in the order Zn, Cu, Ag. We would love to make our list more vast and design a metal activity series or electrochemical series. The competition for electrons between various metals helps us to design a class of cells, named as galvanic cells, in which the chemical reactions become the source of electrical energy. We would study more about these cells in class 12. 8.3 Oxidation number. A less obvious example of electron transfer is realized when hydrogen combines with oxygen to form water by the reaction 2H2 G plus O2 G 2H2O L. 8.18 Though not simple in its approach, yet we can visualize the H atom as going from a neutral 0 state in H2 to a positive state in H2O. The O atom goes from a 0 state in O2 to a negative state in H2O. It is assumed that there is an electron transfer from H2O and consequently H2 is oxidized and O2 is reduced. However, as we shall see later, the charge transfer is only partial and is perhaps better described as an electron shift rather than a complete loss of electron by H and gain by O. What has been said here with respect to equation 8.18 may be true for a good number of other reactions involving covalent compounds. Two such examples of this class of the reactions are H2S plus Cl2 G 2HCl G 8.19 and CH4 G plus 4Cl2 G CCl4 L plus 4HCl G 8.20. In order to keep track of electron shifts in chemical reactions involving formation of covalent compounds, a more practical method of using oxidation number has been developed. In this method, it is always assumed that there is a complete transfer of electron from a less electronegative atom to a more electronegative atom. For example, we rewrite equations 8.18 to 8.20 to show charge on each of the atoms forming part of the reaction 00 plus 122 H2 G plus O2 G 2H2O L 8.21 00 plus 11 H2 S plus Cl2 G 2HCl G 8.22 4 plus 1 0 plus 4 1 plus 1 1 CH4 G plus 4 Cl2 G CCl4 L plus 4 HCl G 8.23. It may be emphasized that the assumption of electron transfer is made for bookkeeping purpose only, and it will become obvious at a later stage in this unit that it leads to the simple description of redox reactions. Oxidation number denotes the oxidation state of an element in a compound ascertained according to a set of rules formulated on the basis that 2019 to 20. (268) Chemistry. Electron pair in a covalent bond belongs entirely to more electronegative element. It is not always possible to remember or make out easily in a compound ion, which element is more electronegative than the other. Therefore, a set of rules has been formulated to determine the oxidation number of an element in a compound ion. If two or more than two atoms of an element are present in the molecule ion such as Na2S2O3Cr2O72, the oxidation number of the atom of that element will then be the average of the oxidation number of all the atoms of that element. We may at this stage state the rules for the calculation of oxidation number. These rules are: 1. In elements, in the free or the uncombined state, each atom bears an oxidation number of 0. Evidently each atom in H2O2Cl2, O3P4S8 Na, Mg, L has the oxidation number 0. 2. For ions composed of only one atom, the oxidation number is equal to the charge on the ion. Thus now plus ion has an oxidation number of +1, Mg2 plus ion, +2, Fe3 plus ion, +3, Cl ion, 1, O2 ion, 2, and so on. In their compounds all alkali metals have oxidation number of +1, and all alkaline earth metals have an oxidation number of +2. Aluminium is regarded to have an oxidation number of +3 in all its compounds. 3. The oxidation number of oxygen in most compounds is 2. However, we come across two kinds of exceptions here. One arises in the case of peroxides and superoxides, the compounds of oxygen in which oxygen atoms are directly linked to each other. While in peroxides, e.g., H2O2, Na2O2, each oxygen atom is assigned an oxidation number of 1. In superoxides, e.g., CO2, RbO2, each oxygen atom is assigned an oxidation number of ½ The second exception appears rarely, i.e. when oxygen is bonded to fluorine. In such compounds e.g., oxygen difluoride, of2, and dioxygen difluoride, O2F2, the oxygen is assigned an oxidation number of +2 and +1, respectively. The number assigned to oxygen will depend upon the bonding state of oxygen, but this number would now be a positive figure only. 4. The oxidation number of hydrogen is +1, except when it is bonded to metals in binary compounds, that is compounds containing two elements. For example, in LiH, Na, and CaH2, its oxidation number is 1. 5. In all its compounds, fluorine has an oxidation number of 1. Other halogens, Cl, Br, and I, also have an oxidation number of 1, when they occur as halide ions in their compounds. Chlorine, bromine and iodine when combined with oxygen, for example in oxoacids and oxoanions, have positive oxidation numbers. 6. The algebraic sum of the oxidation number of all the atoms in a compound must be 0. In polyatomic ion, the algebraic sum of all the oxidation numbers of atoms of the ion must equal the charge on the ion. Thus, the sum of oxidation number of 3 oxygen atoms and 1 carbon atom in the carbonate ion, CO3, 2 must equal 2. By the application of above rules, we can find out the oxidation number of the desired element in a molecule or in an ion. It is clear that the metallic elements have positive oxidation number and non-metallic elements have positive or negative oxidation number. The atoms of transition elements usually display several positive oxidation states. The highest oxidation number of a representative element is the group number for the first two groups and the group number -10, following the long form of periodic table, for the other groups. Thus, it implies that the highest value of oxidation number exhibited by an atom of an element generally increases across the period in the periodic table. In the third period, the highest value of oxidation number changes from 1 to 7 as indicated below in the compounds of the elements. A term that is often used interchangeably with the oxidation number is the oxidation state. Thus in CO2, the oxidation state of carbon is +4, that is also its oxidation number, and similarly the oxidation state as well as oxidation number of oxygen is 2. This implies that the oxidation number denotes the oxidation state of an element in a compound. 2019-20. Redox reactions. The oxidation number state of a metal in a compound is sometimes presented according to the notation given by German chemist Alfred Stock. It is popularly known as Stock notation. According to this, the oxidation number is expressed by putting a Roman numeral representing the oxidation number in parentheses after the symbol of the metal in the molecular formula. Thus aurous chloride and auric chloride are written as Au, I, Cl and Au, 3, Cl3. Similarly, stannous chloride and stannic chloride are written as Sn, 2, Cl2 and Sn, 4, Cl4. This change in oxidation number implies change in oxidation state, which in turn helps to identify whether the species is present in oxidized form or reduced form. Thus, Hg2, I, Cl2 is the reduced form of Hg, 2, Cl2. Problem 8.3 using stock notation, represent the following compounds: Hog4, Tl2O, FeO, Fe2O3, CoI, CO, MnO and MainO2. Solution by applying various rules of calculating the oxidation number of the desired element in a compound. The oxidation number of each metallic element in its compound is as follows. Hog4 has 3 Tl2O, Tl has 1 FeO, Fe has 2 Fe2O, 3 Fe has 3 CoI, Co has 1 CO, Co has 2 MnO, Mn has 2 MainO2, Mn has 4. Therefore, these compounds may be represented as HO, 3, Cl4, Tl2, I, O, Fe, 2, O, Fe2, 3, O3, Co, I, Co, 2, O, Mn, 2, O, Mn, 4, O2. The idea of oxidation number has been invariably applied to define oxidation, reduction, oxidizing agent, oxidant, reducing agent, reductant, and the redox reaction. To summarize, we may say that oxidation, an increase in the oxidation number of the element in the given substance. Reduction, a decrease in the oxidation number of the element in the given substance. Oxidizing agent, a reagent which can increase the oxidation number of an element in a given substance. These reagents are called as oxidants also. Reducing agent, a reagent which lowers the oxidation number of an element in a given substance. These reagents are also called as reductants. Redox reactions, reactions which involve change in oxidation number of the interacting species. Problem 8.4 justify that the reaction 2Co2O S plus Co2S S 6Co S plus SO2 G is a redox reaction. Identify the species oxidized reduced, which acts as an oxidant and which acts as a reductant. Solution. Let us assign oxidation number to each of the species in the reaction under examination. This results in 2 plus 1 2 plus 1 2 0 plus 4 2 2 Co2O S plus Co2S S 6 Co S plus SO2 We therefore conclude that in this reaction copper is reduced from +1 state to 0 oxidation state and sulfur is oxidized from 2 state to +4 state. The above reaction is thus a redox reaction. Group 1st February 2013 14 15 16 17 Element Na MgL Sci PsCl Compound Na Cl MgSO4 Alf 3 Sci-Cl4 P4O10 SF6 Clo4 Highest oxidation +1 +2 +3 +4 +5 +6 +7 Number state of the group element 2019 to 20. (270) Chemistry. Further, Co2O helps sulfur in Co2S to increase its oxidation number. Therefore, Co(I) is an oxidant, and sulfur of Co2S helps copper both in Co2S itself and Co2O to decrease its oxidation number. Therefore, sulfur of Co2S is reductant. 8 March 2001 Types of redox reactions. 1. Combination reactions. A combination reaction may be denoted in the manner A plus B C. Either A and B or both A and B must be in the elemental form for such a reaction to be a redox reaction. All combustion reactions, which make use of elemental dioxygen, as well as other reactions involving elements other than dioxygen, are redox reactions. Some important examples of this category are 00 plus 42C, S, plus O2, G, CO2, G, 8.24, 00 plus 233 Mg, S, plus N2, G, Mg3N2, S, 8.25, 4 plus 10 plus 42 plus 12 CH4, G, plus 2O2, G, CO2, G, plus 2H2O, L, 2. Decomposition reactions. Decomposition reactions are the opposite of combination reactions. Precisely, a decomposition reaction leads to the breakdown of a compound into two or more components, at least one of which must be in the elemental state. Examples of this class of reactions are plus 12002H2O, L, 2H2, G, plus O2, G, 8.26, plus 11002 Na, S, 2 Na, S, plus H2, G, 8.27, plus 1 plus 52 plus 1102 Clo 3, S, 2K close, S, plus 3O2, G, 8.28. It may carefully be noted that there is no change in the oxidation number of hydrogen in methane under combination reactions and that of potassium in potassium chlorate in reaction, 8.28. This may also be noted here that all decomposition reactions are not redox reactions. For example, decomposition of calcium carbonate is not a redox reaction. Plus 2 plus 4 2 plus 2 2 plus 4 2 CaCO3, S, CaO, S, plus CO2, G, 3. Displacement reactions. In a displacement reaction, an ion, or an atom, in a compound is replaced by an ion, or an atom, of another element. It may be denoted as X plus YZ. X Z plus Y. Displacement reactions fit into two categories: metal displacement and non-metal displacement. A. Metal displacement. A metal in a compound can be displaced by another metal in the uncombined state. We have already discussed about this class of the reactions under Section 8 February 2001. Metal displacement reactions find many applications in metallurgical processes in which pure metals are obtained from their compounds in ores. A few such examples are plus 2 plus 6200 plus 2 plus 62 QSO4, AC, plus Zn, S, Q, S, plus ZnSO4, AC, 8.29, plus 5200 plus 22V2O5, S, plus 5Ca, S, 2V, S, plus 5CaO, S, 8.30. Plus 4100 plus 21TCl4, L, plus 2 Mg, S, T, S, plus 2 MgCl2, S, 8.31, plus 320 plus 320 Cr2O3, S, plus 2L, S, L2O3, S, plus 2 Cr, S, 8.32. In each case, the reducing metal is a better reducing agent than the one that is being reduced, which evidently shows more capability to lose electrons as compared to the one that is reduced. B. Non-metal displacement. The non-metal displacement redox reactions include hydrogen displacement and a rarely occurring reaction involving oxygen displacement. 2019-20. 271 Redox reactions. All alkali metals and some alkaline earth metals, Ca, Ca, and Ba, which are very good reductants, will displace hydrogen from cold water. 0 plus 1 2 plus 1 2 plus 1 0 2 Na, S plus 2H2O L 2 now H Ac plus H2 G 8.33 0 plus 1 2 plus 2 2 plus 1 0 Ca S plus 2H2O L Ca O 2 Ac plus H2 G 8.34 Less active metals such as magnesium and iron react with steam to produce the hydrogen gas 0 plus 1 2 plus 2 2 plus 1 0 Mg S plus 2H2O L Mg O 2 S plus H2 G 8.35 0 plus 1 2 plus 3 2 0 2 Fe S plus 3H2O L Fe 2O3 S plus 3H2 G 8.36 Many metals, including those which do not react with cold water, are capable of displacing hydrogen from acids. The hydrogen from acids may even be produced by such metals which do not react with steam. Cadmium and tin are the examples of such metals. A few examples for the displacement of hydrogen from acids are 0 plus 1 1 plus 2 1 0 Zn S plus 2 HCl Ac ZnCl2 Ac plus H2 G 8.37 0 plus 1 1 plus 2 1 0 Mg S plus 2 H close Ac MgCl2 Ac plus H2 G 8.38 0 plus 1 1 plus 2 1 0 Fe S plus 2 HCl Ac FeCl2 Ac plus H2 G 8.39 Reactions 8.37 to 8.39 are used to prepare the hydrogen gas in the laboratory. Here, the reactivity of metals is reflected in the rate of hydrogen gas evolution, which is the slowest for the least active metal Fe, and the fastest for the most reactive metal, Mg. Very less active metals, which may occur in the native state such as silver, Ag, and gold, Au, do not react even with hydrochloric acid. In section 8 February 2001, we have already discussed that the metals zinc, Zn, copper, Cu, and silver, Ag, through tendency to lose electrons show their reducing activity in the order Zn, Cu, Ag. Like metals, activity series also exists for the halogens. The power of these elements as oxidizing agents decreases as we move down from fluorine to iodine in group 17 of the periodic table. This implies that fluorine is so reactive that it can replace chloride, bromide and iodide ions in solution. In fact, fluorine is so reactive that it attacks water and displaces the oxygen of water, plus 120 plus 1102 H2O, L, plus 2F2, G, 4HF, Ac, plus O2, G, 8.40. It is for this reason that the displacement reactions of chlorine, bromine and iodine using fluorine are not generally carried out in aqueous solution. On the other hand, chlorine can displace bromide and iodide ions in an aqueous solution as shown below, 0 plus 1 1 plus 1 1 0 Cl2, G, plus 2 Kbr, Ac, 2 KCl, Ac, plus Br2, L, 8.41, 0 plus 1 1 plus 1 1 0 Cl2, G, plus 2 K, Ac, 2 KCl, Ac, plus I2, S, 8.42. As Br2 and I2 are colored and dissolve in CCl4, can easily be identified from the color of the solution. The above reactions can be written in ionic form as 0110 Cl2, G, plus 2 Br, Ac, 2 Cl, Ac, plus Br2, L, 8.41a, 0110 Cl2, G, plus 2 I, Ac, 2 Cl, Ac, plus I2, S, 8.42b, reactions, 8.41, and 8.42, formed the basis of identifying Br and I in the laboratory through the test popularly known as layer test. It may not be out of place to mention here that bromine likewise can displace iodide ion in solution, 0110 Br2, L, plus 2I, Ac, 2Br, Ac, plus I2, S, 8.43. The halogen displacement reactions have a direct industrial application. The recovery of halogens from their halides requires an oxidation process, which is represented by 2xx2 plus 2e, 8.44. Here X denotes a halogen element. Whereas chemical means are available to oxidize Cl, Br and I, as fluorine is the strongest oxidizing 2019-20. (272) Chemistry agent. There is no way to convert F ions to F2 by chemical means. The only way to achieve F2 from F is to oxidize electrolytically, the details of which you will study at a later stage. For disproportionation reactions, disproportionation reactions are a special type of redox reactions. In a disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. One of the reacting substances in a disproportionation reaction always contains an element that can exist in at least 3 oxidation states. The element in the form of reacting substance is in the intermediate oxidation state, and both higher and lower oxidation states of that element are formed in the reaction. The decomposition of hydrogen peroxide is a familiar example of the reaction, where oxygen experiences disproportionation. +1 1 +1 2 0 2 H2O2, Ac, 2H2O, L, plus O2, G, 8.45. Here the oxygen of peroxide, which is present in one state, is converted to 0 oxidation state in O2 and decreases to 2 oxidation state in H2O. Phosphorus, sulfur and chlorine undergo disproportionation in the alkaline medium as shown below, 0,3 plus 1 P4, S, plus 3O, Ac, plus 3H2O, L, pH3, G, plus 3H2PO2, Ac, 8.46, 0,2 plus 2S8, S, plus 12O, Ac, 4S2, Ac, plus 2S2O32, Ac, plus 6H2O, L, 8.47, 0 plus 1 1Cl2, G, plus 2O, Ac, ClO, Ac, plus Cl, Ac, plus H2O, L, 8.48. The reaction, 8.48, describes the formation of household bleaching agents. The hypochlorite ion, ClO, formed in the reaction oxidizes the color-bearing stains of the substances to colorless compounds. It is of interest to mention here that whereas bromine and iodine follow the same trend as exhibited by chlorine in reaction, 8.48, fluorine shows deviation from this behavior when it reacts with alkali. The reaction that takes place in the case of fluorine is as follows: 2F2, G, plus 2O, Ac, 2F, Ac, plus of 2, G, plus H2O, L, 8.49. It is to be noted with care that fluorine in reaction, 8.49, will undoubtedly attack water to produce some oxygen also. This departure shown by fluorine is not surprising for us, as we know the limitation of fluorine that, being the most electronegative element, it cannot exhibit any positive oxidation state. This means that among halogens, fluorine does not show a disproportionation tendency. Problem 8.5. Which of the following species do not show disproportionation reaction and why? ClO, close O2, close O3 and close O4 also write reaction for each of the species that disproportionates. Solution among the oxoanions of chlorine listed above. Clause O4 does not disproportionate because in this oxoanion chlorine is present in its highest oxidation state, that is, +7. The disproportionation reactions for the other three oxoanions of chlorine are as follows: +1 1 +5 3 ClO2 Cl plus ClO3 plus 3 plus 5 1 6 Clause O2 4 ClO3 plus 2 Cl plus 5 1 plus 7 4 ClO3 Cl plus 3 Clause O4 Problem 8.6 suggest a scheme of classification of the following redox reactions: A. N2 G plus O2 G 2 No G B 2 Pb number 3 2 S 2 PbO S plus 4 number 2 G plus O2 G C Na S plus H2O L now H AC plus H2 G D 2 No 2 G plus 2 O AC number 2 AC plus number 3 AC plus H2O L 2019 to 20. 273 Redox reactions solution in reaction A. The compound nitric oxide is formed by the combination of the elemental substances, nitrogen and oxygen. Therefore, this is an example of combination redox reactions. The reaction B involves the breaking down of lead nitrate into three components. Therefore, this is categorized under decomposition redox reaction. In reaction, the paradox of fractional oxidation number. Sometimes, we come across with certain compounds in which the oxidation number of a particular element in the compound is in fraction. Examples are C3O2, where oxidation number of carbon is 4,3, Br3O8, where oxidation number of bromine is 16,3, and Na2S4O6, where oxidation number of sulfur is 2.5. We know that the idea of fractional oxidation number is unconvincing to us, because electrons are never shared transferred in fraction. Actually, this fractional oxidation state is the average oxidation state of the element under examination, and the structural parameters reveal that the element for whom fractional oxidation state is realized is present in different oxidation states. Structure of the species C3O2, Br3O8 and S4O6 to reveal the following bonding situations: +2 0 +2 O is equal to C is equal to C asterisk is equal to C is equal to O. Structure of C3O2, carbon suboxide. Structure of Br3O8, tribromooctaoxide. Structure of S4O62, tetrathanate ion. The element marked with asterisk in each species is exhibiting the different oxidation state, oxidation number, from rest of the atoms of the same element in each of the species. This reveals that in C3O2, 2 carbon atoms are present in +2 oxidation state each, whereas the third one is present in 0 oxidation state and the average is 4,3. However, the realistic picture is +2 for 2 terminal carbons and 0 for the middle carbon. Likewise in Br3O8, each of the 2 terminal bromine atoms are present in +6 oxidation state and the middle bromine is present in +4 oxidation state. Once again the average, that is different from reality, is 16,3. In the same fashion, in the species S4O62, each of the 2 extreme sulfures exhibits oxidation state of +5 and the 2 middle sulfures as 0. The average of 4 oxidation numbers of sulfures of the S4O62 is 2.5, whereas the reality being +500 and +5 oxidation number respectively for each sulfur. We may thus, in general, conclude that the idea of fractional oxidation state should be taken with care and the reality is revealed by the structures only. Further, whenever we come across with fractional oxidation state of any particular element in any species, we must understand that this is the average oxidation number only. In reality, revealed by structures only, the element in that particular species is present in more than one whole number oxidation states. Fe3O4, Mn3O4, Pb3O4 are some of the other examples of the compounds, which are mixed oxides, where we come across with fractional oxidation states of the metal atom. However, the oxidation states may be in fraction as in O2 plus and O2 where it is plus a half and half respectively. C. Hydrogen of water has been displaced by hydride ion into the hydrogen gas. Therefore, this may be called as displacement redox reaction. The reaction, D, involves disproportionation of number 2 plus 4 state into number 2 plus 3 state and number 3 plus 5 state. Therefore reaction, D, is an example of disproportionation redox reaction. 2019-20. (274) Chemistry Problem 8.7 Why do the following reactions proceed differently? Pb3O4 plus 8H closed 3 PbCl2 plus Cl2 plus 4H2O and Pb3O4 plus 4HNO3 2 Pb. Number 3. 2 plus PbO2 plus 2H2O solution. Pb3O4 is actually a stoichiometric mixture of 2 mol of PbO and 1 mol of PbO2. In PbO2, lead is present in plus 4 oxidation state, whereas the stable oxidation state of lead in PbO is plus 2. PbO2 thus can act as an oxidant, oxidizing agent, and, therefore, can oxidize Cl ion of HCl into chlorine. We may also keep in mind that PbO is a basic oxide. Therefore, the reaction Pb3O4 plus 8H closed 3 PbCl2 plus Cl2 plus 4H2O can be split into two reactions, namely 2 PbO plus 4H closed 2 PbCl2 plus 2H2O, acid-base reaction, plus 4 1 plus 2 0 PbO2 plus 4H close PbCl2 plus Cl2 plus 2H2O, redox reaction. Since HNO3 itself is an oxidizing agent, therefore, it is unlikely that the reaction may occur between PbO2 and HNO3. However, the acid-base reaction occurs between PbO and HNO3 as 2 PbO plus 4HNO3 2 Pb. Number 3. 2 plus 2H2O. It is the passive nature of PbO2 against HNO3 that makes the reaction different from the one that follows with HCl. 8 March 2002 Balancing of redox reactions. Two methods are used to balance chemical equations for redox processes. One of these methods is based on the change in the oxidation number of reducing agent and the oxidizing agent, and the other method is based on splitting the redox reaction into two half reactions, one involving oxidation and the other involving reduction. Both these methods are in use, and the choice of their use rests with the individual using them. A. Oxidation number method. In writing equations for oxidation-reduction reactions, just as for other reactions, the compositions and formulas must be known for the substances that react and for the products that are formed. The oxidation number method is now best illustrated in the following steps. Step 1. Write the correct formula for each reactant and product. Step 2. Identify atoms which undergo change in oxidation number in the reaction by assigning the oxidation number to all elements in the reaction. Step 3. Calculate the increase or decrease in the oxidation number per atom and for the entire molecule ion in which it occurs. If these are not equal, then multiply by suitable numbers so that these become equal. If you realize that two substances are reduced and nothing is oxidized or vice versa, something is wrong. Either the formulas of reactants or products are wrong or the oxidation numbers have not been assigned properly. Step 4. Ascertain the involvement of ions. If the reaction is taking place in water, add H plus or O ions to the expression on the appropriate side so that the total ionic charges of reactants and products are equal. If the reaction is carried out in acidic solution, use H plus ions in the equation. If in basic solution, use O ions. Step 5. Make the numbers of hydrogen atoms in the expression on the two sides equal by adding water, H2O, molecules to the reactants or products. Now, also check the number of oxygen atoms. If there are the same number of oxygen atoms in the reactants and products, the equation then represents the balanced redox reaction. Let us now explain the steps involved in the method with the help of a few problems given below. Problem 8.8. Write the net ionic equation for the reaction of potassium dichromate, 6, K2Cr2O7 with sodium sulfite, Na2SO3, in an acid solution to give chromium, 3, ion and the sulfate ion. 2019-20. 275 Redox reactions solution. Step 1. The skeletal ionic equation is Cr2O72 Ac plus SO32 Ac Cr3 plus Ac plus SO42 Ac. Step 2. Assign oxidation numbers for Cr and S plus 62 plus 42 plus 3 plus 62 Cr2O72 Ac plus SO32 Ac Cr Ac plus SO42 Ac. This indicates that the dichromate ion is the oxidant and the sulfite ion is the reductant. Step 3. Calculate the increase and decrease of oxidation number and make them equal. From suite P-2 we can notice that there is change in oxidation state of chromium and sulfur. Oxidation state of chromium changes from +6 to +3. There is decrease of +3 in oxidation state of chromium on right hand side of the equation. Oxidation state of sulfur changes from +4 to +6. There is an increase of +2 in the oxidation state of sulfur on right hand side. To make the increase and decrease of oxidation state equal, place numeral 2 before chromium ion on right hand side and numeral 3 before sulfate ion on right hand side and balance the chromium and sulfur atoms on both the sides of the equation. Thus we get +6 2 +4 2 +3 Cr2O72 Ac +3 SO32 Ac 2 Cr3 plus Ac +6 2 3 SO42 Ac. Step 4. As the reaction occurs in the acidic medium, and further the ionic charges are not equal on both the sides, add 8H plus on the left to make ionic charges equal. Cr2O72 Ac plus 3 SO32 Ac plus 8H plus 2 Cr3 plus Ac plus 3 SO42 Ac. Step 5. Finally, count the hydrogen atoms and add appropriate number of water molecules, i.e., 4H2O, on the right to achieve balanced redox change. Cr2O72 Ac plus 3 SO32 Ac plus 8H plus Ac 2 Cr3 plus Ac plus 3 SO42 Ac plus 4H2O. L. Problem 8.9. Permanganate ion reacts with bromide ion in basic medium to give manganese dioxide and bromate ion. Write the balanced ionic equation for the reaction. Solution. Step 1. The skeletal ionic equation is MnO4 Ac plus Br Ac MnO2 S plus Bro3 Ac. Step 2. Assign oxidation numbers for Mn and Br plus 7 1 plus 4 plus 5 MnO4 Ag plus Br Ag MnO2 S plus Bro3 Ag. This indicates that permanganate ion is the oxidant and bromide ion is the reductant. Step 3. Calculate the increase and decrease of oxidation number, and make the increase equal to the decrease. Plus 7 1 plus 4 plus 5 2 MnO4 Ag plus Br Ag 2 MnO2 S plus Bro3 Ag. Step 4. As the reaction occurs in the basic medium, and the ionic charges are not equal on both sides, add 2 O ions on the right to make ionic charges equal. 2 MnO4 Ag plus Br Ag 2 MnO2 S plus Bro3 Ag plus 2 O Ag. Step 5. Finally, count the hydrogen atoms and add appropriate number of water molecules, i.e. 1 H2O molecule, on the left side to achieve balanced redox change. 2 MnO4 Ag plus Br Ag plus H2O L 2 MnO2 S plus Bro3 Ag plus 2 O Ag. B. Half reaction method. In this method, the two half equations are balanced separately and then added together to give balanced equation. Suppose we are to balance the equation showing the oxidation of Fe2 plus ions to Fe3 plus ions by dichromate ions, Cr2O7, 2 in acidic medium, wherein Cr2O72 ions are reduced to Cr3 plus ions. The following steps are involved in this task. Step 1. Produce unbalanced equation for the reaction in ionic form. Fe2 plus Ag plus Cr2O72 Ag Fe3 plus Ag plus Cr3 plus Ag 8.50 2019-20. (276) Chemistry. Step 2. Separate the equation into half reactions, plus 2 plus 3 oxidation half, Fe2 plus Ag Fe3 plus Ag 8.51 plus 6 2 plus 3 reduction half, Cr2O72 Ag Cr3 plus Ag 8.52. Step 3. Balance the atoms other than O and H in each half reaction individually. Here the oxidation half reaction is already balanced with respect to Fe atoms. For the reduction half reaction, we multiply the Cr3 plus by 2 to balance Cr atoms. Cr2O72 Ag 2 Cr3 plus Ag 8.53. Step 4. For reactions occurring in acidic medium, add H2O to balance O atoms and H plus to balance H atoms. Thus, we get Cr2O72 Ag plus 14H plus Ag 2 Cr3 plus Ag plus 7H2O L 8.54. Step 5. Add electrons to one side of the half reaction to balance the charges. If need be, make the number of electrons equal in the two half reactions by multiplying one or both half reactions by appropriate number. The oxidation half reaction is thus rewritten to balance the charge. Fe2 plus Ag Fe3 plus Ag plus E 8.55. Now in the reduction half reaction there are net 12 positive charges on the left hand side and only 6 positive charges on the right hand side. Therefore, we add 6 electrons on the left side. Cr2O72 Ag plus 14H plus Ag plus 6E2 Cr3 plus Ag plus 7H2O L 8.56. To equalize the number of electrons in both the half reactions, we multiply the oxidation half reaction by 6 and write as 6 Fe2 plus Ag 6 Fe3 plus Ag plus 6E 8.57. Step 6. we add the two half reactions to achieve the overall reaction and cancel the electrons on each side. This gives the net ionic equation as 6Fe2 plus Ac plus Cr2O72 Ac plus 14H plus Ac 6Fe3 plus Ac plus 2Cr3 plus Ac plus 7H2O L 8.58. Step 7. Verify that the equation contains the same type and number of atoms and the same charges on both sides of the equation. This last check reveals that the equation is fully balanced with respect to number of atoms and the charges. For the reaction in a basic medium, first balance the atoms as is done in acidic medium. Then for each H plus ion, add an equal number of O ions to both sides of the equation. Where H plus and O appear on the same side of the equation, combine these to give H2O. Problem 8.10 Permanganate 7 ion main O4 in basic solution oxidizes iodide ion I to produce molecular iodine I2 and manganese 4 oxide main O2. Write a balanced ionic equation to represent this redox reaction. Solution Step 1. First we write the skeletal ionic equation, which is main O4, Ac, plus I, Ac, MnO2, S, plus I2, S. Step 2. The two half reactions are 1,0 oxidation half, I, Ac, I2, S, plus 7 plus 4 reduction half, main O4, Ac, MnO2, S. Step 3. To balance the I atoms in the oxidation half reaction, we rewrite it as 2I, Ac, I2, S. Step 4. To balance the O atoms in the reduction half reaction, we add two water molecules on the right, main O4, Ac, main O2, S, plus 2, H2O, L. To balance the H atoms, we add 4 H plus ions on the left, main O4, Ac, plus 4 H plus, Ac, MnO2, S, plus 2 H2O, L. As the reaction takes place in a basic solution, therefore, for 4 H plus ions, we add 4 O ions to both sides of the equation, main O4, Ac, plus 4 H plus, Ac, plus 4O, Ac, main O2, S, plus 2H2O, L, plus 4O, Ac, replacing the H plus and O ions with water, 2019-20. 277 Redox reactions. The resultant equation is main O4, Ac, plus 2H2O, L, main O2, S, plus 4O, Ac. Step 5. In this step we balance the charges of the two half reactions in the manner depicted as 2I, Ac, I2, S, plus 2E main O4, Ac, plus 2H2O, L, plus 3E MnO2, S, plus 4O, Ac. Now to equalize the number of electrons, we multiply the oxidation half reaction by 3 and the reduction half reaction by 2. 6I, Ac, 3I2, S, plus 6E2 main O4, Ac, plus 4H2O, L, plus 6E2 MnO2, S, plus 8O, Ac. Step 6. Add two half reactions to obtain the net reactions after cancelling electrons on both sides. 6I, Ac, plus 2 MnO4, Ac, plus 4H2O, L, 3I2, S, plus 2 MnO2, S, plus 8O, Ac. Step 7. A final verification shows that the equation is balanced in respect of the number of atoms and charges on both sides. 8 March 2003 Redox reactions. As the basis for titrations in acid-base systems, we come across with a titration method for finding out the strength of one solution against the other using a pH-sensitive indicator. Similarly, In redox systems, the titration method can be adopted to determine the strength of a reductant oxidant using a redox-sensitive indicator. The usage of indicators in redox titration is illustrated below. In one situation, the reagent itself is intensely colored, e.g., permanganate ion, MainO4. Here MainO4 acts as the self-indicator. The visible endpoint in this case is achieved after the last of the reductant, Fe2+ or C2O42, is oxidized and the first lasting tinge of pink color appears at MnO4 concentration as low as 10.6 mol dm3, 10.6 mol L1. This ensures a minimal overshoot in color beyond the equivalence point, the point where the reductant and the oxidant are equal in terms of their mole stoichiometry. 2. If there is no dramatic autocolor change, as with MainO4 titration, there are indicators which are oxidized immediately after the last bit of the reactant is consumed, producing a dramatic color change. The best example is afforded by Cr2O72, which is not a self-indicator, but oxidizes the indicator substance diphenylamine just after the equivalence point to produce an intense blue color, thus signaling the endpoint. 3. There is yet another method which is interesting and quite common. Its use is restricted to those reagents which are able to oxidize ions, say, for example, Cu2Cu2+, Ac, plus 4I, Ac, Cu2I2, S, plus I2, Ac, 8.59. This method relies on the facts that iodine itself gives an intense blue color with starch and has a very specific reaction with thiosulfate ions, S2O32, which 2 is a redox reaction, I2, Ac, plus 2S2O32, Ac, 2I, Ac, plus S4O62, Ac, 8.60. I2, though insoluble in water, remains in solution containing Ke as Ke3. On addition of starch after the liberation of iodine from the reaction of Cu2 plus ions on iodide ions, an intense blue color appears. This color disappears as soon as the iodine is consumed by the thiosulfate ions. Thus, the endpoint can easily be tracked and the rest is the stoichiometric calculation only. 8 March 2004 Limitations of concept of oxidation number. As you have observed in the above discussion, the concept of redox processes has been evolving with time. This process of evolution is continuing. In fact, in recent past the oxidation process is visualized as a decrease in electron density and reduction process as an increase in electron density around the atom S involved in the reaction. 8.4 Redox reactions and electrode processes. The experiment corresponding to reaction 8.15 can also be observed if zinc rod is dipped in copper sulfate solution. The redox reaction takes place and during the reaction 2019 to 20. 278 Chemistry. Zinc is oxidized to zinc ions and copper ions are reduced to metallic copper due to direct transfer of electrons from zinc to copper ion. During this reaction heat is also evolved. Now we modify the experiment in such a manner that for the same redox reaction transfer of electrons takes place indirectly. This necessitates the separation of zinc metal from copper sulfate solution. We take copper sulfate solution in a beaker and put a copper strip or rod in it. We also take zinc sulfate solution in another beaker and put a zinc rod or strip in it. Now reaction takes place in either of the beakers and at the interface of the metal and its salt solution in each beaker both the reduced and oxidized forms of the same species are present. These represent the species in the reduction and oxidation half reactions. A redox couple is defined as having together the oxidized and reduced forms of a substance taking part in an oxidation or reduction half reaction. This is represented by separating the oxidized form from the reduced form by a vertical line or a slash representing an interface, e.g. solid solution. For example, in this experiment the two redox couples are represented as Zn2 plus Zn and Cu2 plus Cu. In both cases, oxidized form is put before the reduced form. Now we put the beaker containing copper sulfate solution and the beaker containing zinc sulfate solution side by side, Fig 8.3. We connect solutions in two beakers by a salt bridge, a U-tube containing a solution of potassium chloride or ammonium nitrate usually solidified by boiling with agar and later cooling to a jelly-like substance. This provides an electric contact between the two solutions without allowing them to mix with each other. The zinc and copper rods are connected by a metallic wire with a provision for an ammeter and a switch. The setup as shown in Fig. 8.3 is known as Daniell cell. When the switch is in the off position, no reaction takes place in either of the beakers and no current flows through the metallic wire. As soon as the switch is in the on position, we make the following observations. 1. The transfer of electrons now does not take place directly from Zn to Cu2+, but through the metallic wire connecting the two rods as is apparent from the arrow which indicates the flow of current. 2. The electricity from solution in one beaker to solution in the other beaker flows by the migration of ions through the salt bridge. We know that the flow of current is possible only if there is a potential difference between the copper and zinc rods known as electrodes here. The potential associated with each electrode is known as electrode potential. If the concentration of each species taking part in the electrode reaction is unity, if any gas appears in the electrode reaction, it is confined to 1 atmospheric pressure, and further the reaction is carried out at 298 K, then the potential of each electrode is said to be the standard electrode potential. By convention, the standard electrode potential, E of hydrogen electrode, is 0.00 volts. The electrode potential value for each electrode process is a measure of the relative tendency of the active species in the process to remain in the oxidized reduced form. A negative E means that the redox couple is a stronger. Fig. 8.3 The setup for Daniell cell. Electrons produced at the anode due to oxidation of Zn travel through the external circuit to the cathode where these reduce the copper ions. The circuit is completed inside the cell by the migration of ions through the salt bridge. It may be noted that the direction of current is opposite to the direction of electron flow. 2019-20. 279 Redox reactions. Reaction, oxidized form plus reduced form, EVF2, G, plus 2E2F2.87 CO3 plus E CO2 plus 1.81 H2O2 plus 2H plus 2E2H2O 1.78 MnO4 plus 8H plus 5E Mn2 plus 4H2O 1.51 AO3 plus 3E AO, S, 1.40 Cl2, G, plus 2E2Cl 1.36 Cr2O 72 plus 14H plus 6E2Cr3 plus 7H2O 1.33 O2, G, plus 4H plus 4E2H2O 1.23 MnO2, S, plus 4H plus 2EMN2 plus 2H2O 1.23 Br2 plus 2E2 Br 1.09 No 3 plus 4H plus 3E No, G, plus 2H2O 0.972 Hg2 plus 2 EHG22 plus 0.92 Ag plus EAG, S, 0.80 Fe3 plus E Fe2 plus 0.77 O2, G, plus 2H plus 2E, H2O2 0.68 I2, S, plus 2E2 I 0.54 Q plus EQ, S, 0.52 Q2 plus 2 EQ, S, 0.34 AgCl, S, plus EAG, S, plus Cl 0.22 AgBr, S, plus EAG, S, plus Br 0.102 H plus 2 EH2, G, 0.00 Pb2 plus 2 EPB, S, 0.13 SN2 plus 2 ESN, S, 0.14 Ne2 plus 2 E Ne, S, 0.25 Fe2 plus 2 E Fe, S, 0.44 Cr3 plus 3 ECr, S, 0.74 Zn2 plus 2 EZn, S, 0.76 2H2O plus 2 EH2, G, plus 2O 0.83 L3 plus 3 EL, S, 1.66 Mg2 plus 2 EMG, S, 2.36 Na plus E Na, S, 2.71 Ca2 plus 2 ECa, S, 2.87 K plus EK, S, 2.93 Li plus E Li, S, 3.05. Increasing strength of oxidizing agent, increasing strength of reducing agent 1. A negative E means that the redox couple is a stronger reducing agent than the H plus H2 couple. 2. A positive E means that the redox couple is a weaker reducing agent than the H plus H2 couple. Table 8.1. The standard electrode potentials at 298 K ions are present as aqueous species and H2O as liquid. Gases and solids are shown by G and S respectively. Reducing agent than the H plus H2 couple. A positive E means that the redox couple is a weaker reducing agent than the H plus H2 couple. The standard electrode potentials are very important and we can get a lot of other useful information from them. The values of standard electrode potentials for some selected electrode processes, reduction reactions, are given in Table 8.1. You will learn more about electrode reactions and cells in Class 12, 2019-20. Chemistry summary. Redox reactions form an important class of reactions in which oxidation and reduction occur simultaneously. 3-tier conceptualization with classical, electronic and oxidation number, which is usually available in the texts, has been presented in detail. Oxidation, reduction, oxidizing agent, oxidant, and reducing agent, reductant, have been viewed according to each conceptualization. Oxidation numbers are assigned in accordance with a consistent set of rules. Oxidation number and ion-electron method both are useful means in writing equations for the redox reactions. Redox reactions are classified into 4 categories: combination, decomposition, displacement, and disproportionation reactions. The concept of redox couple and electrode processes is introduced here. The redox reactions find wide applications in the study of electrode processes and cells. Exercises 8.1. Assign oxidation number to the underlined elements in each of the following species: A, Na2PO4, B, NaHSO4, C, H4P2O7, D, K2MnO4, E, CaO2, F, NaBH4, G, H2S2O7, H, Cul, SO4, 2.12H2O 8.2 What are the oxidation number of the underlying elements in each of the following and how do you rationalize your results? A. Ke3, B. H2S4O6, C. Fe3O4, D. CH3CH2O, E. CH3Co 8.3 Justify that the following reactions are redox reactions. A. Co S plus H2, G, Co S plus H2O, G, B, Fe2O3, S, plus 3 Co, G, 2 Fe, S, plus 3 Co2, G, C, 4BCl3, G, plus 3 Lil4, S, 2B2H6, G, plus 3 LiCl, S, plus 3 AlCl3, S, D, 2K, S, plus F2, G, 2K plus F, S, E, 4NH3, G, plus 5O2, G, 4NO, G, plus 6H2O, G, 8.4 Fluorine reacts with ice and results in the change, H2O, S, plus F2, G, HF, G, plus HOF, G, justify that this reaction is a redox reaction. 8.5 Calculate the oxidation number of sulfur, chromium and nitrogen in H2SO5, Cr2O72 and number 3. Suggest structure of these compounds. Count for the fallacy. 8.6 Write formulas for the following compounds. A. Mercury, 2. Chloride, B. Nickel, 2. Sulfate, C. Tin, 4. Oxide, D. Thallium, I. Sulfate, E. Iron, 3. Sulfate, F. Chromium, 3. Oxide 8.7 Suggest a list of the substances where carbon can exhibit oxidation states from 4 to +4 and nitrogen from 3 to +5. 8.8 While sulfur dioxide and hydrogen peroxide can act as oxidizing as well as reducing agents in their reactions, ozone and nitric acid act only as oxidants. Why? 8.9 Consider the reactions. A. 6CO2, G, plus 6H2O, L, C6H12O6, AC, plus 6O2, G, 2019-20. 281 Redox reactions, B, O3, G, plus H2O2, L, H2O, L, plus 2O2, G. Why it is more appropriate to write these reactions as A. 6CO2, G, plus 12H2O, L, C6H12O6, AC, plus 6H2O, L, plus 6O2, G, B, O3, G, plus H2O2, L, H2O, L, plus O2, G, plus O2, G. Also suggest a technique to investigate the path of the above, A, and B, redox reactions. 8.10 The compound AgF2 is unstable compound. However, if formed, the compound acts as a very strong oxidizing agent. Why? 8.11 Whenever a reaction between an oxidizing agent and a reducing agent is carried out, a compound of lower oxidation state is formed if the reducing agent is in excess and a compound of higher oxidation state is formed if the oxidizing agent is in excess. Justify this statement giving 3 illustrations. 8.12 How do you count for the following observations? A. Though alkaline potassium permanganate and acidic potassium permanganate both are used as oxidants, yet in the manufacture of benzoic acid from toluene we use alcoholic potassium permanganate as an oxidant. Why? Write a balanced redox equation for the reaction. B. When concentrated sulfuric acid is added to an inorganic mixture containing chloride, we get colorless pungent smelling gas HCl, but if the mixture contains bromide then we get red vapor of bromine. Why? 8.13 Identify the substance oxidized, reduced, oxidizing agent and reducing agent for each of the following reactions. A. 2AgBr S plus C6H6O2 Ac 2Ag S plus 2HBr Ac plus C6H4O2 Ac B HCHO L plus 2 Ag NH3 2 plus Ac plus 3O Ac 2 Ag S plus HCO Ac plus 4 NH3 Ac plus 2 H2O L C HCHO L plus 2 Cu2 plus Ac plus 5O Ac Cu2O S plus HCO Ac plus 3 H2O L D N2H4 L plus 2 H2O2 L N2 G plus 4 H2O L E Pb S plus PbO2 S plus 2 H2SO4 Ac 2 PbSO4 S plus 2 H2O L. 8.14 Consider the reactions 2S2O32 Ac plus I2 S S4O62 Ac plus 2I Ac S2O32 Ac plus 2Br2 L plus 5H2O L 2SO42 Ac plus 4Br Ac plus 10H plus Ac. Why does the same reductant, thiosulfate, react differently with iodine and bromine? 8.15 Justify giving reactions that among halogens, fluorine is the best oxidant and among hydrohalic compounds, hydroiodic acid is the best reductant. 8.16 Why does the following reaction occur? XHO64 Ac plus 2F Ac plus 6H plus Ac XHO3 G plus F2 G plus 3H2O L. What conclusion about the compound Na for XHO6, of which XHO64 is a part, can be drawn from the reaction? 8.17 Consider the reactions A. H3PO2 Ac plus 4AgNO3 Ac plus 2H2O L H3PO4 Ac plus 4Ag S plus 4HNO3 Ac B H3PO2 Ac plus 2QSO4 Ac plus 2H2O L H3PO4 Ac plus 2Q S plus H2SO4 Ac C C6H5CHO L plus 2 Ag NH3 2 plus Ac plus 3O Ac C6H5Q Ac plus 2 Ag S plus 4 NH3 Ac plus 2 H2O L D C6H5CHO L plus 2 Q2 plus Ac plus 5O Ac. No change observed. 2019-20. (282) Chemistry. What inference do you draw about the behavior of Ag plus and Cu2 plus from these reactions? 8.18 Balance the following redox reactions by ion-electron method. A. MnO4 Ac plus I Ac MainO2 S plus I2 S in basic medium. B. MainO4 Ac plus SO2 G Mn2 plus Ac plus HSO4 Ac in acidic solution. C. H2O2 Ac plus Fe2 plus Ac Fe3 plus Ac plus H2O L in acidic solution. D. Cr2O72 plus SO2 G Cr3 plus Ac plus SO42 Ac in acidic solution. 8.19 Balance the following equations in basic medium by ion-electron method and oxidation number methods and identify the oxidizing agent and the reducing agent. A. P4 S plus O Ac pH3 G plus HPO2, Ac, B, N2H4, L, plus close O3, Ac, No, G, plus Cl, G, C, Cl2O7, G, plus H2O2, Ac, close O2, Ac, plus O2, G, plus H plus 8.20. What sorts of informations can you draw from the following reaction? Cn, 2, G, plus 2O, Ac, Cn, Ac, plus CNO, Ac, plus H2O, L, 8.21. The Mn3 plus ion is unstable in solution and undergoes disproportionation to give Mn2 plus, main O2 and H plus ion. Write a balanced ionic equation for the reaction. 8.22. Consider the elements, Cas, Na, I and F. I. Identify the element that exhibits only negative oxidation state. B. Identify the element that exhibits only positive oxidation state. C. Identify the element that exhibits both positive and negative oxidation states. D. Identify the element which exhibits neither the negative nor does the positive oxidation state. 8.23. Chlorine is used to purify drinking water. Excess of chlorine is harmful. The excess of chlorine is removed by treating with sulfur dioxide. Present a balanced equation for this redox change taking place in water. 8.24. Refer to the periodic table given in your book and now answer the following questions. A. Select the possible non-metals that can show disproportionation reaction. B. Select 3 metals that can show disproportionation reaction. 8.25. In Ostwald's process for the manufacture of nitric acid, the first step involves the oxidation of ammonia gas by oxygen gas to give nitric oxide gas and steam. What is the maximum weight of nitric oxide that can be obtained starting only with 10.00 g of ammonia and 20.00 g of oxygen? 8.26. Using the standard electrode potentials given in the table 8.1, predict if the reaction between the following is feasible. A. Fe3 plus, Ac, and I, Ac, B, Ag plus, Ac, and Q, S, C, Fe3 plus, Ac, and Q, S, D, Ag, S, and Fe3 plus, Ac, E, Br2, Ac, and Fe2 plus, Ac. 2019-20. 283. Redox reactions. 8.27. Predict the products of electrolysis in each of the following. I. An aqueous solution of AgNO3 with silver electrodes. 2. An aqueous solution AgNO3 with platinum electrodes. 3. A dilute solution of H2SO4 with platinum electrodes. 4. An aqueous solution of CuCl2 with platinum electrodes. 8.28. Arrange the following metals in the order in which they displace each other from the solution of their salts. L, Q, Fe, Mg and Zn. 8.29. Given the standard electrode potentials, K plus K is equal to 2.93 V, Ag plus Ag is equal to 0.80 V, Hg2 plus Hg is equal to 0.79 V, Mg2 plus Mg is equal to 2.37 V, Cr3 plus Cr is equal to 0.74 V. Arrange these metals in their increasing order of reducing power. 8.30. Depict the galvanic cell in which the reaction Zn, S, plus 2H